Okay, welcome to the Unit 7 Thermodynamics and Gases. This is day 1. So at this point you should have already watched the Part 1 Play Pause It demo, and you should have filled out the pre-demo questions. You also should have filled out the data in the table, the initial and final temperatures, and you should have answered the post-demo questions. The other thing you should have done at this point is actually filled in the notes that we're going to go over, so then that way you don't have to fill them in as you go, with exception of some annotations and some examples. But if you haven't done that, that's okay. You can pause the video as needed to fill in the notes. Okay, so in this unit we're going to talk about thermodynamics, which is the study of energy transfer. And that's super important because a lot of what scientists look at, and also engineers, are things that involve the transfer of energy. So from a chemist's perspective, during a physical change, whether that's boiling, melting, or condensation, or a chemical reaction, energy can transfer to or from the system and surroundings in two ways. One as work and the other as heat. Now, when I say system means the part that we're focusing on. So that's usually, if we're dealing with a chemical reaction, that will be the chemical reaction. And the surroundings would be everything else that's in contact with that system. So for example, if you are performing a reaction inside of a beaker, the surroundings, part of the surroundings will be the beaker. If the reaction is being done in an aqueous solution in a liquid, then the surroundings would also be the water that the reaction is happening in. So the system is the part that you're really focusing on, and surroundings, everything else that's in contact with it. In this unit, the only transfer of energy that we're going to focus on is heat. So we're really just focusing on this part right here. We won't look at work. The symbol for heat is Q, and the units are capital J, which are called joules. You might want to end that annotation in. Or it can be in kilojoules, calories, or kilocalories. Now, these kilocalories are actually the units that you see on the back of the nutritional information on the back of cereal boxes or whatever. It's given a capital C there, but those are kilocalories. The equation for heat is Q is equal to MC delta T, which means heat equals to mass times specific heat capacity times change in temperature. You can also remember it using this mnemonic QMCAT, since the delta looks like a capital A, so that would spell cat. So QMCAT is another way of memorizing it. So Q is equal to heat, as I said, and the units are joules. Mass is grams. Specific heat capacity units are joules per grams degrees Celsius. And delta T is the change in temperature, which you get from the final temperature minus the initial temperature. And your temperatures can be measured either in degrees Celsius or capital K, which is Kelvin, since they have the same scale. And you're taking the change in temperature. So for this case, you can use degrees Celsius or Kelvin. The delta T would still be the same. All right. So we know how to measure heat. Let's go into a little specifically about what the heat capacity is. So the heat capacity, or specific heat capacity, really describes the amount of energy needed to raise the temperature of a substance 1 degree Celsius. And you notice we're using heat capacity and specific heat capacity. And there's a difference between them. And the difference really is that the heat capacity is for a given sample. So its units are in joules per degree Celsius. And the equation for heat then would be Q equals heat capacity, which is given a capital C symbol, times delta T. On the other hand, specific heat capacity uses a lowercase c, and it's per 1 gram, and the units are joules per grams degrees Celsius. And the equation is Q is equal to MC delta T. So the key thing with heat capacity, since it's for whatever sample that you have, since the amount of your sample will change, the amount of heat, or the amount of your sample could be different, the amount of heat that's lost or gained would be different. And so, for example, a larger sample would require more heat to change its temperature. So with that being the case, C, or heat capacity, capital C, is not constant and it will depend on the sample, whereas specific heat capacity is a constant since it's per 1 gram. And so therefore we oftentimes will be using specific heat capacity. We won't really use heat capacity much, but it's important to know that there is a difference. Heat capacity, you won't see mass in the units, and there's no mass in the equation. Whereas specific heat capacity, you see mass in the units, and there's mass in the equation. Okay, so the key thing about heat capacity or specific heat capacity, the main thing is that the larger that value is, the more heat energy can be absorbed by the substance before its temperature increases. So the larger the heat capacity, the greater the delta T. And let's go ahead now and just use this Q equals MC delta T equation to calculate heat to get a little bit familiar with it, and then we'll come back to this concept later when revisiting the demo. All right, so in this first example we have how much heat is needed to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius, and they give us the specific heat capacity. All right, so we have our mass, and we have our TI, initial temperature, and our TF. And we have our little c, our specific heat capacity. And we want to calculate the heat. So I know the equation is Q is equal to MC delta T. And I know I'm given my mass. So I can go ahead and plug that in. It's in grams, 250 grams. No need to convert units. I'm also given my specific heat capacity, 4.18 joules per grams degrees Celsius. And I'm giving the initial and final temperature. So I can use this information to solve for my delta T. So let's go ahead and do that over here. The delta T will equal to TF minus TI. So that would be equal to 98 minus 22. And when we do that, we get 76. Great. So now that I have that information, we can go ahead and calculate by multiplying all that together to solve for Q. Okay, so